Great. So the last talk for the day will be Weihua Hu, who's also a PhD candidate at Stanford Computer Science Department. Weihua is the lead on the Open Graph Benchmark, which is a suite of data sets for measuring progress in machine learning on graphs. So go ahead, Weihua.
Yeah, thank you, Yuri, for the introduction. So I'm Weihua, and I'm excited to talk about Open Graph Benchmark Large-Scale Challenge. And this is a project about developing common benchmark datasets for machine learning on graphs. So the starting point of this project is the realization that benchmarks are really important. And historically, this has been exemplified by the success of ImageNet and MS-COCO in computer vision, and the success of SQuAD and GLUE benchmark in the field of natural language processing. Concretely, these challenging and realistic benchmark datasets has really driven a lot of methodological innovations in the field. For example, in the computer vision community, ImageNet is really successful, and many methods have been developed to achieve better and better accuracy, as shown in this figure. And at each accuracy improvement, very innovative methods have been developed, such as the introduction of convolutional networks, making it deeper, and the use of more unlabeled data to further improve the performance. So from this history, we learned that in order to evaluate machine learning on graphs, and in order to advance the research in the machine learning with graphs, it is critical for us to develop diverse, challenging, and realistic benchmark datasets for machine learning on graphs. However, if we look at the existing graph benchmark datasets, there are a lot of issues. The first issue is that the datasets or the graphs are really small. They are too small to be realistic, and also they are too small that it's difficult to compare different models in a statistically significant way. The second issue is that the experimental protocol is not unified. Different data splits or different evaluation metrics are used for different papers, and it's very hard to directly make a model comparison. The third issue is that these data splits follow conventional random splits. Basically, given an entire data set, just randomly split the training data into training validation tests and this essentially assumes that the test data that we're going to make prediction on follows the same distribution as training data, while in real world, we always observe this distributional shift. And the model performance evaluated on this random split might be too optimistic. And for all these three issues, it was really hard to rigorously evaluate graph machine learning models, and therefore it's very hard to make research advance in graph machine learning. To resolve these issues, in May 2020, we introduced Open Graph Benchmark, in short OGB, which is a collection of realistic and diverse benchmark datasets for machine learning on graphs. So all the datasets and the descriptions are available on our webpage, ogb.stanford.edu. We have a paper that describes our benchmark that's published in last year's NeurIPS. And we have a GitHub repository that contains all the code to use the data and all the baseline code that we use to benchmark different models. So OGB datasets are really diverse. They are diverse in three axes, in terms of tasks, domains, and scales. In terms of tasks, we prepare the three core graph machine learning tasks, node property prediction, link property prediction, and graph property prediction. In terms of domains, we have a graphs dataset from natural science domain like chemistry, biology. We have graphs from social and information networks, and also knowledge graph as well as the computer source code. And these domains often offer rich node and edge features that the machine learning model can leverage. And in terms of the dataset size, we prepare graphs that are small, medium, and large. And here, the small is still much larger than any of the existing benchmark. And the small datasets can be used to quickly iterate the different ideas, while medium and large graphs provide a real challenge of scaling up graph machine learning model to large graphs. So in total, OGB includes 15 data sets from diverse domains and tasks as shown here. And since the introduction of OGB last year, many methods have been developed on our data set. Over 300 public leaderboard submissions have been made, and the drastic accuracy improvement over many data sets has been observed. So here are 2 examples of OGB data sets, and we see there's a sharp increase in the accuracy on both of the data sets, and a lot of innovative methods have been developed in order to achieve that. Now, in order to really yield a breakthrough and further advance the field of graph machine learning, we need an even larger scale graph benchmark. This is because historically, this breakthrough in natural language or computer vision has been achieved by training a bigger and advanced model on large data. And these bigger and advanced models really benefit from large data, and we think this making the data set larger would enable the development of such model, like a deeper and more expressive GNNs. And therefore, such models can achieve a very impressive results that's impossible with a smaller data set. Also, I want to emphasize that machine learning on large-scale graph is technically challenging and requires methodological innovations. For example, training GNNs on large graph requires non-trivial mini-batch sampling of nodes and edges. So it really also involves some methodological innovation. In order to push this frontier of large-scale graph machine learning, for this year's ACM KDD Cup, which is one of the largest prestigious machine learning competition in the world, we provide a set of 3 challenging large-scale graph data sets. So again, the webpage containing all the information about this KDD Cup is available on the ogb.stanford.edu, KDD Cup 2021. We have paper describing our challenge, and we have a GitHub repository that have all the code for the baseline and the data set. So this OGB large-scale challenge has really attracted huge attention from the community. So we got over 500 team registrations across the globe. For the initial test submissions, there are 143 teams submitted to this initial test submission, and 123 teams submitted to the final test submission. And in terms of institution, they are really balanced between academia and industry. So the key characteristics of this large-scale challenge data sets are that they are orders of magnitude larger than any of the existing data sets, including OGB, original OGB. So we prepared this 3 data set, prediction at the level of nodes, links, and graphs. For example, for the first data set, the number of nodes is over 200 million, and the number of edges is over 1 billion. And others are also quite large. And each data set is really practically relevant. And what I'm going to do now is to briefly introduce each of the data set and show you the performance improvement that has been made during the 3-month period of KDD Cup 2021. So the first data set that we prepared is a node-level classification task called MAG 240 million. It's a heterogeneous academic graph. So we have 3 kinds of nodes within this graph. We have paper nodes, author nodes, and institution nodes. Papers nodes cite with each other. So there's an edge for that. Author nodes writes paper nodes, and the author's node is affiliated with some institution nodes. So there is a heterogeneous graph, and the task here is to predict the subject area of papers situated in heterogeneous graph. So because this paper is a node, so it's a node classification problem. It's about, and the number of classes here is over 100. So it's a really challenging fine-grained classification task. And here's the performance improvement made over the KDD Cup. And here the x-axis represents the rank in the final test submission, and the y-axis represents the accuracy, the higher the better. And the green one is the best baseline, which we implemented using the state-of-the-art graph neural networks. And we see that within this 3 months period, winners have already achieved more than 6% accuracy improvement over our best baseline, which is quite impressive. The second data set we prepared is called for link level prediction, WikiKG 90 million. And in knowledge, and it's a knowledge graph data set extracted from the entire Wikidata. And the issue with this knowledge graph is that the coverage issue. There are many facts that are missing in the knowledge graph. For example, for Geoffrey Hinton, we may know, he's a person and he graduated from King's College, but this fact about the birthplace of Geoffrey Hinton might be missing from the knowledge graph. So the task here is to impute the triplets, to predict that Geoffrey Hinton, the birthplace of Geoffrey Hinton, based on the other facts stored in the knowledge graph. And here is again a significant accuracy improvement have been made. Now the metric is MRR, the higher the better, and we see that the winners really outperform our best baseline method by more than 10%. The final data set is about the graph level prediction called PCQM 4 million. It's a molecular graph. The task here is to predict, given molecular graphs, we want to predict an important quantum chemistry property of molecule called Homo-Lumo gap. And it's basically a graph regression task. And here it's very practically relevant in drug and material discovery because in these domains, in order to calculate this Homo-Lumo gap, we often need to run expensive quantum calculation which could take hours per molecule. But if we use machine learning model, we can do this within much faster, within much less than 1 second. And therefore, we can apply this model to screen, to predict property of much larger number of molecules and find a better molecule for our downstream task. And on this again, so the metric here is a mean absolute error, prediction error, the error between the ground truth Homo-Lumo gap and the predicted Homo-Lumo gap, so the lower the better. And we see that the winners again significantly outperform our pretty strong baseline models. So I've seen this, a lot of performance improvement have been made. So what has driven this performance improvement? So here's a summary. And in fact, it's really promising that many novel techniques have been developed for our OGB large-scale challenge graphs. For example, in order to handle large graph node classification, new mini-batch sampling technique for heterogeneous graph has been developed. Others are new label propagation method using GNNs has been developed. New knowledge graph embedding models have been developed. And also new self-supervised learning methods for GNN has been developed. A lot of methodological innovation has been made. One thing that I want to emphasize is that people indeed find that the deeper, bigger, and more expressive GNN outperforms less expressive one. So for the molecule data set, this is very salient. For our baseline, the number of GNN layers that we use is 5 layers, while the winners use 11 up to 40 layers of GNN to achieve their best performance. And in terms of number of parameters, our baseline used 6.7 million parameters, while the winners use 50 million up to 450 million number of parameters for GNNs. And we do observe that bigger models indeed perform better on large data set. And also, there's a trend in making GNNs more expressive. So the winner of the molecule classification benchmark uses a transformer-style fully connected message passing. So usually, we perform message passing on the input graph that is sparse. But transformer style basically consider this fully connected graph, and at each round of message passing, each node can receive message from all the rest of the node. And it's more expressive than the original GNN. So we've seen a lot of great progress, and now I want to outline the outlook for the future. And we hope the community will continue to use our OGB large-scale challenge LC datasets to develop new methods. We still think there are a lot of room for improvement. And we are also updating these datasets based on the lessons from the KDD Cup to facilitate further research advances, specifically making some datasets more challenging and including more information like 3D structure of molecules. We not only for the methodological and model and algorithm innovation, we also hope to facilitate the development of efficient machine learning systems, like a more easy-to-use frameworks and more efficient hardware to handle large-scale graphs. So to conclude, large-scale graphs are really ubiquitous in real-world applications like recommender system, knowledge graphs, and this molecule task. But they are really challenging to handle. And in order to push this limit, push the frontier of large-scale graph ML, in this OGB large-scale challenge, we provide a set of 3 unprecedentedly large graph datasets. And we deploy these datasets at the KDD Cup. And we observe many innovative methods have been developed on these data sets. Thank you very much.
This is great. Do we have any questions from the audience? If not, I wanted to ask you a question. What are your next steps? How do you see the development of graph benchmarks going forward?
Yeah, that's a great question. I think, first of all, like this even larger scale benchmark might be good. And also, I feel like this dynamic nature of the graph can be the next step to go. Like currently, we are assuming this static graph, but this edge and nodes might have a more fine-grained timestamp, and the handling those will be important.
So you think having data sets that evolve over time and being able to have dynamic models that can capture the dynamics of the graph?
Yes.
Yeah. Super. Another question is, as you see these large-scale data sets, how do you think the connection with the training frameworks will play out for us to be able to scale this out?
Right. So, right. I think really, like as data set becomes large, really designing a good training framework becomes more and more important. And currently, like the kind of most promising paradigm is to do neighbor sampling. And I'm expecting, there are more sophisticated techniques to sample neighbors, and this framework I think should also support those different sophisticated neighbor sampling techniques.
Okay. Thank you. And then the next question I wanted to ask you is in terms of different application domains. So far, OGB has mostly focused on some chemistry applications, some applications in knowledge graphs. Can you talk more about that?
Yes, right. So in terms of application domains, like in the original OGB, we cover a lot of application domain. In large-scale challenge, we cover 3. But it's definitely interesting to, for example, include the large-scale bipartite graph that seems to be missing currently in recommender systems.
Recommender systems seem to be one application. Good. And then one thing I wanted to ask you, so you also organized the KDD Cup this year that was kind of had an amazing reception in the community, hundreds of submissions, many different teams as we saw from your slides. What would you say are some most surprising learnings from the competition, from the, let's say, approaches people used to win the competition or to perform well in those tasks?
Right. That's a great question. So there are a lot of learning, but one learning, I think first learning is that the power of the community is super strong. It's like we observe like unexpectedly huge accuracy improvement within just 3 months. And another learning is that people start to develop more and more effort to scale up this expressive model to large graph to achieve better performance. So that's it's good to see that direction and achieve good performance.
And then I have a bit of a philosophical question. So do you think in this field, is it possible to build a universal GNN, or is it really about taking a particular problem and developing an architecture for it?
Right, yeah, that's a great question. I think there could definitely be some universal GNN for example, maybe for molecules or recommender system, but maybe it's hard to develop GNN that work both for knowledge graph and the academic graph and the molecules simultaneously. If there's some similarity, we may be able to share some knowledge. But some graphs are too different, and we might need to more specific approach to each of them.
Okay, great. And then there's an interesting question online, which is about, OGB is a great way to push forward the research, and most of your metrics that you considered are model accuracy metrics.
Yes.
Have you thought about also like scalability, running speed, all these other metrics that in practice are also very important when we think about practical deployments?
Yeah, that's a really great question. Like for the KDD cup, we only focus on the accuracy, but in practice, we can consider following this down benchmark developed Stanford, we can say how much time or resource we require to achieve this threshold accuracy. And I think that's an important next step.
Good. Since we have a few minutes, another question is, somebody's asking, how would I develop a model bigger than the MAG model?
Bigger than?
Than the MAG. So I assume this is the Microsoft Academic Graph. How do I develop a graph bigger than the Microsoft Academic Graph?
Right.
So people are asking for the code we used to generate or to build these data sets.
I see. Right, I guess this one was, basically we just download this Microsoft Academic Graph and pre-process it. It involves some engineering, but it can be done using normal Python and just do it for 1 week and we can get that graph.
Or you write some C++ code.
We do have some C++ code, I think. Yeah.
Awesome.
But yeah, mostly Python is fine.
Awesome, great. Question from the audience here? No question? Good, then let's thank Wei Hua and then move to the panel. Thank you, Wei Hua, again.
Thank you.